So, big O notation. I know, it sounds super technical, maybe even a little intimidating, right? But trust me, it's the secret language that decides how fast or how slow every single app on your phone runs. Today, we're going to pull back the curtain and make it all make sense. You know the feeling. We've all been there. You're scrolling for your photos, your playlist gets massive, and all of a sudden, it just grinds to a halt. That lag, it's not random. It's usually baked right into the code, and Big O is what tells us exactly why it's happening. If you remember one thing, make it this phrase. This is the heart of it. Big O isn't about timing a piece of code with a stopwatch. It's all about predicting what happens to performance as the amount of data you throw at it, what programmers just call N, gets bigger and bigger. It's like a universal report card for how efficient code is. Okay, so how does this whole measuring stick actually work? Before we dive into some really cool examples, we just need to get on the same page with 3 simple rules that make it all click. First off, it's totally machine independent. We don't care if you're on a brand new supercomputer or a 10-year-old laptop. We're looking at the recipe, not the oven. That's why we focus on the number of steps an algorithm takes, not how many seconds. And finally, we sweat the big stuff and ignore the small stuff. If an operation takes n steps plus like 2 tiny extra steps, we just round down and call it n. We're looking at the overall trend. All right, this is where it really gets good. The absolute best way to understand this is to see 2 different approaches to the exact same problem side by side. Get ready for that aha moment. So the job is pretty simple. Add up all the numbers from 1 to some number n. Now, function A does it the way you or I might do it. It just loops through one by one, adding each number to the total. But function B, well, function B is clever. It uses a little math trick to get the answer instantly. And we're not going to play around with small numbers here. We're going to really put these functions to the test. Let's set n to 1 million. Both of them have to add up every number from 1 all the way to 1,000,000. And wow, the results are just staggering. Function A, our slow and steady loop, takes about 1,000,000 steps to finish the job. But function B, the smart one, it takes 3 steps, a multiplication, an addition, and a division. That's it, 1,000,000 versus 3. So in the language of Big O, we'd say function A is O of n, which stands for linear time. This is probably one of the most common types you'll see. It just means that the work grows in a perfect straight line with the data. You double the data, you double the steps. Makes sense. And our amazing function B, that's O of 1, or constant time. Now, the 1 doesn't literally mean 1 step. It just means the number of steps is constant. It never changes. Whether n is 10, a million, or a trillion, it's always those same 3 steps. This, my friends, is the holy grail. It's the gold standard for efficiency. So we've seen O of n and O of 1, but they're not the only players in the game. There's a whole family of these things, creating a full performance hierarchy. And the best way to get a feel for them is to actually see what they look like. Okay, I want you to picture a simple graph in your head. Along the bottom axis, you've got the amount of data, n, increasing as you go to the right. And then up the side, you have the amount of time or steps it takes to get things done. Got it? Okay, so on that graph, our hero, O of 1, is a perfectly flat horizontal line. No matter how much data you add, the time stays the same. Beautiful. Our O of n function is a nice, predictable 45-degree line. More data, more time, perfectly proportional. But then you get to things like O of n squared, or quadratic time. And this is where things get really bad. The line starts to curve up, and then it just goes almost vertical. This is what happens when you have, say, a loop running inside of another loop. And I mean, look at how fast that spirals out of control. If you have 1,000 items, a linear O of n algorithm takes 1,000 steps, no problem. But an O of n squared algorithm, that's 1,000 times 1,000. That's 1,000,000 steps. As the data gets bigger, performance just falls off a cliff. So that's a lot of different letters and numbers and curves. How are you supposed to remember all of them? Well, I find the easiest way is to think of it like a report card you'd get in school. It's a pretty simple grading system. O of 1, constant time. That's an A+. Straight A's, best in class. Then you have O of log n, which is incredibly fast for searching. That's a solid B. A reliable friend O of n, linear time, gets a C. It's average, it gets the job done. But then we fall off a cliff. O of n squared is a definite F. It's a failing grade. And something like O of n factorial time, that is so catastrophically bad, you don't just fail, you get expelled. Now, here's a really crucial bit of nuance. Big O is all about how things perform at scale. For a really, really small amount of data, sometimes a bad algorithm, like O of n squared, can actually be faster because it has less overhead. So the report card matters most when you know your data is going to grow. Context is everything. And that kind of brings us to our final thought. In today's world of massive datasets, AI, and planet-spanning networks, the difference between an A+ and an F grade isn't just a grade on a whiteboard. It's the difference between an app you love and one you delete. It can cost companies millions in server fees, waste incredible amounts of energy, and lose them customers forever. So as the data piles up, the real cost of that F is something we all end up paying for.